This is the video presentation of our report entitled
Quantification of the tension variation in stretched string due to linear thermal expansion with fluctuating thermal systems resulting in shifts in frequency.
Good morning, secondary science education students. I am Dr. Hill, and this is Dr. Montgomery. Today, we'll be presenting to you the science behind the tuning of the electric guitar,
Namely, how temperature affects this tuning.
our tested problem. Here in Australia, a guitarist may step out onto stage and encounter a range of problems to do with temperature. Primarily, stage lights, the heat of an Australian summer at festivals, and large crowds can all contribute large amounts of heat to the environment. If this heat is affecting the strings, there is the possibility that it may affect the tuning.
Our aim is to find out if changing temperatures do indeed result in a change of the frequency of guitar strings, and to what extent that this change occurs. As I'm sure many of you already know, when you heat a solid, it expands. This is because you are giving the particles more kinetic energy, and thus they separate from one another. If this is performed in a solid, the solid expands and becomes larger. Or in our case, a string, the string becomes longer, as you can see here.
So as you may have gathered by now, we are testing guitar strings, and we are using primarily this equation. In this equation, F refers to the frequency of the string, which is the pitch of the note that you hear. High frequencies are high-pitched sounds, low frequencies are low-pitched sounds, or bass. Frequency is equal to half of the length of the string. In our case, this is from the top nut of the guitar to the bottom, which is called the bridge. So, frequency equals half times length times the square root of the tension, how tightly the string is stretched, divided by U, which is mass per unit length, which is talking about how much the string weighs per centimetre or metre. So if we're talking about a very thick steel cable, that's going to be a very high mass per unit length. Or if we're talking about something like an elastic band or a piece of hair, it's going to have a very low mass per unit length. So, frequency is equal to half L, longer strings will give us lower frequencies, times the square root of tension. Low tension gives us low frequencies, high tension gives us high frequencies, divided by U. And U can mean thick strings and thin strings, thicker strings giving us low frequencies, thinner strings giving us high frequencies.
Now it's time for you to play with the lackey bands we supplied you with.
Glenn, stop that. So, using the lackey bands that we have provided you on your desk, I want you to just have a quick play around while we're explaining the next concept to you, trying with longer length, getting a higher frequency, shorter length, lower frequency, and try varying up the amount of tension. There's a frequency there, but if we keep the length the same and introduce more string, which gives us a lower tension, we have a lower note.
Science!
Oh, sorry, I didn't see that. So you may be wondering, how are we going to test this? Well, that's a great question. You better come with me. I'll show you in my box. So, let's have a look at the setup. As you can see, we have our electric bass set up here in our insulated wooden box. We're using 3 100-watt bulbs that pump out a stack of heat to take the internal temperature of the box up, which is being monitored by our digital thermometer here, which has its contact on the inside to measure internal air temperature. What you may realize is the other strings have been taped down so they do not vibrate when the string we are testing is percussed. And there is a highly technical device here that we've constructed out of Lego that percusses the string. And this has been specially designed so that when the box is closed, we can test the string by pushing that, and the string is sounded, and we can test through the computer. The electrical signal from the guitar is sent through the red lead.
This red lead then connects to this overdrive pedal connected to this personal computer, or computational software of calculating the frequency. Science! Now that we've had a look at Michael's amazing box, let's talk a little bit about our procedure.
The first step of the procedure is placing the bass guitar within the enclosed box. At this stage, the lights are off, but for demonstrative purposes, we're going to just leave the lights on so you can see what's going on. The string is tuned to as close to perfect frequency as possible. We then record this and the reference temperature on our digital thermometer, which you can see there, into Microsoft Excel, and that is our reference point as frequency and temperature is concerned. Then the lid of the box is closed. We'll just leave it open because it's prettier that way. And we watch the temperature soar on our temperature gauge, which is external to the box, and we use our Lego technical percussion device to hit the strings from outside of the box because that stick pokes up through the lid. We track the temperature over about an hour and track the frequencies with the respective temperatures, and eventually we derive a graph in Microsoft Excel using our frequency analysis software.
In equation 1, we already know the frequency, the length, and the string thickness, so we can use this equation 1 to find the only variable that we don't know, which is tension. Substituting our value for tension, we can then use the other variables that we already know and find that the length of the string unstretched, as if nothing was acting on it.
Then finally, the hairy part of our equation is equation 3. This relates a tension change as a factor using our unstretched length of string to show, given the ratio of the wood frame of the guitar expanding and the steel string of the guitar expanding, what sort of tension change we'll get. And to demonstrate on this lackey band, we know the wood frame of the guitar, my fingers, will only expand by a slight fraction of the amount that the steel string expands. So I'm going to add length to the steel string within the frame, which produces a lower frequency. So we take the decrease in tension in the string derived from the ratio, and we put it back into equation number 1 as the new tension and find the new frequency after the heat has expanded the guitar.
Science! The most obvious trend in our results, as you can see in this graph, is a negative correlation between frequency and temperature. The strength of this linear trend is shown by our R² value, which is close to 1, meaning our test results line up almost perfectly, showing the direct linear relationship between these two variables. This means that we can confidently say a linear relationship exists between frequency and temperature. We also calculated theoretical values using the equations we explained previously and plotted them on the graph. As you can see, they match quite closely, once again leading us to believe this correlation is no mere coincidence, and that an increase in temperature does indeed result in a decrease in frequency due to the thermal expansion of the metal strings.
So we've done all of the tests, we've done the theoretical calculations, but let's take it right back to the question. What does it all mean? What does it mean for the guitarist standing on stage with the temperature change? In our test results, we have tested that a 20-degree temperature change for the smallest string on a bass guitar equaled a frequency drop from 98 Hz to 95.5 Hz, which might not sound much, but if you listen to the difference on these two guitars, which have been tuned to those frequencies, you can really hear it. Can you imagine if a guitarist was playing that note and a keyboard, who doesn't change tune, was playing the same note? You could definitely hear the difference. And that concludes our report. Signing out from Dr. Hill and Dr. Montgomery. We hope to see you again next time for some more science!